Welcome back, dear friends. Now we are going to discuss few more basic terminologies. Okay, so we saw ambidentate ligands also. Okay, now we will discuss here next hour. That is fifth basic terminologies. That is say chelating ligands. What about that? Say chelating chelating ligands. So what will be these chelating ligands? Here, chelating ligands are those. Okay, it is regarding with polydentate ligands. Okay, so what will happen? Say some polydentate ligands. Okay, some polydentate ligands bond to central metal atom with their donor site to form a close ring. Okay, polydentate ligand they are bonding with central metal atom to form a close ring. Okay, that we can call it as a what chelating ligands. Okay, so see here how we can represent this and say chelating ligands how we can represent beta. As you know beta, suppose this oxalato ion, okay, oxalato ion, as you know this oxalato ion when it is bonded with this central metal atom, okay, bonded with this central metal atom forming as like this, see they are trying to forming ring here, okay, CO and here what, say 2O4 2 minus, yes or no, means like that they are cording, okay, so here whatever this we can call it as a chelating ligands. What we can call it as a chelating ligands. Whatever this oxalate ion, it has a property to form a chelating ligand, and what will be here forming, and we call it as a here. These are what chelates. What whatever forming here we call it as a what chelates. So see here one of the important most part of the regarding these chelating ligands or chelates is what chelates are more stable, chelates are far more stable than other simple complexes. Okay, chelates chelates are far more stable, okay, more stable than other simple complexes, ठीक है, then other simple complexes, and whatever the stability of these chelates, okay, can be explained on the basis of entropy, can be explained on the basis of what entropy change. Okay, so how we can say as a entropy change, suppose here it is, as you know, it is a metal, and here what, and here suppose bidentate ligands are there. Okay, here ligands are there, okay, now suppose here what, first bidentate ligands are there, which beta bidentate ligands are here, and here also bidentate ligands are there, okay. Now what will happen when this bidentate ligand is replaced by monodentate ligand, then automatically entropy of that metal ion it's, or we can say entropy of that complex is increase. So increase in entropy, therefore what beta, yes, therefore there that chelates are what more stable, that chelates are what beta more stable. Okay, so here, and consequently what will happen, yes, consequently entropy also will increase, understood. So it is very much important. Okay, and we can say that chelates are what, that chelates are more stable, okay. Now see here whatever we are discussing next part, so we will discuss here next part also, concentrate on this next part. See, regarding this chelating ligands, one more important part we can arrange here. Okay, so see here whatever that one more important part, as you know, you studied in that organic chemistry also. Okay, Okay, what you studied, whatever chelates, okay, whatever chelates means whatever chelates which form 5 or 6 membered ring are more stable than the other chelates. Okay, means whatever 5 or 6 membered ring, okay, 5 or 6 membered ring are more stable than 4 or 7 membered ring, because in 5 or 6 membered ring there is a what zero angle strain. Okay, now like that also here in these chelates also, whatever they are 5 or 6 membered ring chelates are more stable. Okay, now we will see discuss here whatever fifth, okay, sorry, here our number 6 is oxidation number. Okay, oxidation number. Now see, oxidation number, how we can calculate regarding your this complex. Okay, oxidation number of central metal atom. Central metal atom. Okay, so we can write here the charge present on central metal atom in the complex is called as its oxidation number. Means charge present on central metal atom, we can call it as a what? Oxidation number. Okay, so we will take here some oxidation number also. So say suppose K4, yes, K4 FeCN6. Suppose it is the one of the complex. Okay, so we have to take here what? We have to take here oxidation number. So K4 here, as you know, potassium is what? +4 oxidation number. Okay, potassium is what? Always +1. Okay, and cyanide is what? -1. Okay, and we have to calculate the oxidation number of this iron here. So here 4 potassium, so that's why here what will happen? +4 plus here iron we don't know, so X it is plus cyanide is what? Cyanide, yes, cyanide is what? Each cyanide ion is -1, so here 6, therefore -6 is equal to 0. If there is a charge over here, then we have to write instead of 0 here. Okay, so beta X is equal to what? Obviously +2. Therefore iron here oxidation number is what? +2. Understood? So suppose if you are considering next second, we will discuss here first over. Now suppose second example. Okay, so see second example, CuNH3 4, okay, and SO4. So what will happen here? Say we have to calculate the oxidation number of this central metal atom. Okay, so copper we don't know, so we can call it as X. So ammonia, as you know, here what? Yes, ammonia पर कोई charge नहीं है, so here what? 0. Okay, plus G, as you know, sulfate is what? Yes, sulfate is what? Beta -2. Sulfate ion, SO4 2 minus. Plus here -2 is equal to 0. Therefore beta X is equal to what? +2. Therefore whatever copper oxidation number here, how much? +2. I hope you understood this. Now see here, suppose if you are considering, okay, next say third, we will take as an example of third in oxidation number. Iron beta here, iron, okay, iron, then EDTA, iron, then EDTA, and here what? Minus. And then we have to calculate the oxidation number of this central metal atom. So as you know in EDTA, so basically you must know, or we already discussed whatever iron, okay, whatever EDTA, okay. So EDTA is what? Ethylene diamine tetraacetate. So acetate, okay. So on this acetate, as you know, total charge how much? 4 minus. So here X plus, we don't know what is the charge on this central metal atom X. If we, that's why we are considering as a what? X plus. So EDT how much? -4 is equal to this -1. Therefore X is equal to what beta? Yes, plus 3 you will get here answer. Okay, now suppose, okay, so see here we will discuss as in case of like that compound. Okay, say fourth one K3Fe, yes, K3Fe CN6, K3Fe CN6. So here also these are what central metal atoms, so plus 3 because each potassium charge plus 1, so total 3 are there, so plus 3 plus x plus minus 6 is equal to 0, therefore x is equal to what? Plus 3, understood? So these are very much important, so like that we can calculate oxidation number, understood? I hope you understood this all. Okay, so we will move towards next. Okay, these are what our oxidation number. I hope you wrote in your notes. Okay, you have to revise this frequently. Okay, now we will discuss what is the coordination number. Okay, coordination number. Now pay attention carefully. What is the coordination number? It is what? See, what is the coordination number? It is the number of coordinated bond with the ligand with central metal atom in that complex compound. In that what? Complex compounds. So we call it as a what? Coordination number. Whatever number of coordinated bonds which of the ligand forms with central metal atom. So see, very much simple coordination number. Suppose I will write here one complex, say PT, okay, PTNH3 2 plus, okay. So coordination number means how many ligands, okay, how many ligands. Ligand means what? Here ammonia is ligand, okay. How many ligands are directly bonded with this central metal atom? We call it as a what? Coordination number of that complex. So here coordination number of this complex, how much? Yes, total 4, because this ammonia is what? Monodentate ligand. Suppose if you are considering second example, so you can write second example also. See here K4, yes, K4FeCN6. Okay, so here beta coordination number how much? Yes, how many ligands directly attached with this central metal atom? 6, understood? So third we can write here third, say as like this CrC2O4 thrice, okay, CrC2O4 thrice. So beta here how much coordination number? Yes, coordination number here 6. Why 6? Because what will happen, whatever this Cr, okay, whatever this Cr, your central metal atom, means basically this C2O4 is what? Bidentate ligand, so it will join. So it will join as like this oxalate, okay. Here what? C2O4 OX is what? C2O4 OX is what? Sorry, OX is what? Your oxalate ion. Oxalate we can write like this also. OX means it takes 2 donor sites, that's why it is what? Bidentate ligand. So here total bidentate, so therefore for 3 how much? 6, therefore coordination number how much regarding your this complex here C2O4 thrice is 6, because it bidentate, so 2 3 is 6, therefore coordination number is 6. Now see here fourth one, okay, so fourth one here PT, okay, PT here DMG twice 4 minus, okay. So what will be the coordination number? Yes, coordination number is what? Beta 4, because this DMG dimethyl glyoxime is what? Dimethyl glyoxime is bidentate ligand, so bi means here 2 into 2 4, therefore coordination number how much here? Yes, coordination number how much? Here 4. I hope you understood this. Understood. See, now we will discuss here a few important points regarding coordination number. Okay, so see here, with the help of coordination number, we can predict geometry and hybridization of that complex also. Okay, geometry as well as hybridization. See, as like this, we can write. We will make one chart. No issues. See, coordination number. I am writing only CN. Okay. Now hybridization. See, beta hybridization. Okay. Now see here, geometry also I am writing. Understood? Coordination hybridization with geometry. See. So coordination number 2. Then hybridization is what? Yes, SP and geometry we can write is linear. Okay. When coordination number 4. Okay, at that time two possibilities are there. It's P3, so P3 is what? Yes, tetrahedral. And regarding your coordination number 4, we can write DSP2 also, means hybridization we will get DSP2 also. So at that time what? Yes, square planar. Okay. Square planar. Now when coordination number is 6, yes, when coordination number is 6, so at that time here also what? Two possibilities, that is as like this is P3D2 and D2. Okay, D2 is P3. Okay, is P3D2 and what? D2 is P3. But here geometry for both, it is what? Say, that is octahedral. Means beta this we already discussed. Okay, you already learned this, you already deal this whatever geometry and hybridization also in our topic, that is chemical bonding and molecular structures. Okay, so better you know, and with the help of this it is revised also. Understood? So it is very much basic information regarding this coordination number. Okay, so now we will discuss most important part. Now here our basic terminologies are over. Okay, now one of the most important part we will discuss. No doubt, whatever we are going to we are discussing here, there each and every point is important. Okay, and we have to keep in mind, we have to remove frequently notes, we have to work on that. Okay, practice is very much important for this topic, means every topic. Okay, see, that is whatever next point, that is effective atomic number. So you can write as a heading, yes, effective atomic number, in short EAN, effective atomic number. Okay, so see here, effective atomic number. So effective atomic number, so as you know beta, effective nuclear charge and all. Okay, so effective nuclear charge, so effective atomic number, it is related to our atomic number, that is Z. So we will directly concentrate on, means very much important part here. What is the formula of this? EAN is equal to, so write down beta, Z minus oxidation number plus 2 into what? Coordination number. Okay, so as you know, Z is what? Atomic number. Where Z is what? Atomic number. ON is what? Oxidation number. CN is what? Coordination number. This thing you know better. Okay, so with the help of one example we will solve, we will calculate effective atomic number of that complex. Ready? So see here, effective atomic number. Suppose here, if we will take one complex FeCN6, FeCN6 3 minus. So here, as you know, here you means you must calculate here oxidation number of this Z. You know Z means atomic number of this here, whatever complex they gave with central metal atom, that atomic number you must know. Z is atomic number. So Fe atomic number how much? 26. Coordination number, yes, here how much? 6 total. And we have to calculate charge also. Okay, means here oxidation number also we have to calculate. So see, we will put up here Z is what? Yes, 26. Okay, minus oxidation number. So FeCN6 3 minus. Okay, so we can write here as a x plus minus 6 is equal to minus 3. Therefore x is equal to what, beta? Plus 3. So minus 3 plus 2 into coordination number how much? 6. So beta, how much you will get answer here? Yes, you will get answer here how much? 35. Means En, whatever effective atomic number of this complex. Okay, how much beta? Yes, how much here? 35. Now whatever stability of this complex can be explained on the basis of En. Okay, so see here, the complex in which En of the central metal atom is equal to the atomic number of the next inert gas is more stable. Okay, it's very much important, this statement. The En of the central metal atom is equal to the atomic number of the next inert gas is more stable. Suppose if we will take here a second example, means mostly we will get here what? Nearest or next what? Inert gas atomic number. So regarding this 26, so what will be the nearest beta? Inert gas? Yes. Okay, as you know, inert gas is here Hena, Nena or Karina, Sekirani. Okay, so see here atomic number 2. Okay, here 10, 18, 36, 54 and what? 86. Okay, now nearest atomic number with this 26 or 36 means near about we got here. Okay, so we will discuss another example. Fe, yes, Fe CO5. Okay, Fe CO5. So can you calculate here whatever En of this? Yes, calculate with the help of this formula. Okay, it is easy. So iron, yes, Z is what beta? 26 minus oxidation number here, as you know, this carbonyl, or we can in general carbon monoxide also we can call. Okay, but whenever we are getting a name, whenever we are dealing with name, so what will be the name? Pentacarbonyl iron. Okay, pentacarbonyl iron. Okay, 0. So there is no charge on this carbonyl, therefore here what? Iron oxidation number in this complex 0, plus 2 into coordination number how much? 5. Yes, so 26 plus this 10, 36 means it is stable. Means En for this above complex is what? 36. I hope you understood. This all part. Understood. So we will deal here one more example. Okay. So say one more example we will discuss. Ready? So see, one more example regarding this K2. Okay, third we can write a third example for EA in K2 PtCl6. So K2 PtCl6. Okay, so atomic number of platinum is what? 78. They may already give you, okay, atomic number of this K2PtCl6. Platinum, whatever atomic number is, how much? Yes, 78. So can you put up the values? So Z is what? Z is here 78 atomic number minus oxidation number. Okay, what will be the oxidation number here, beta? See how we can calculate. K2 plus 2 plus x plus minus 6 is equal to 0. Therefore x is equal to what? 4. Understood. So Z atomic number 78 minus 4 plus 2 into how much? 6. Okay, then obviously what you will get the calculation here? Yes, 86. Understood. So here how much, beta? 86. This much very much means like that it is very much easy. Okay, easy to understand this effective atomic number. Okay, now we will discuss. Okay, now we will discuss next part. See, writing a formula of an coordination compound, coordination complex. Okay, see, chemical formula of coordination compound. How we can write this? Okay, say basically there are some rules. Okay, writing the formula of complex or writing the formula of that coordination compound. Okay, see, writing the formula of complex, or we can say what? Coordination compounds. So here first is what? Cation is written first followed by anion. Cation is written first followed by, yes, followed by anion. Okay, second you can write in square bracket complex, in square bracket complex, in square bracket complex is written first, complex is written first, then central atom, then ligand, then central metal atom, then ligand. Okay, like that we have to follow order. Okay, so we can write is as a means whatever ligand we are going to write that follow, we have to order like this: anionic, then neutral, then what? Cationic. Okay, ligand in the following order: first anionic, neutral, and cationic. We already saw that. Okay, now third we can write, if two ligands are of same type, then they are arranged in alphabetically order. So alphabetically order like this. Suppose ammonia and water are there. Okay, so as you know, this NH3 is what? We call it as yes, ammonia, and here what? H2. So in this topic of our coordination compound, water For water, we call it as a, yes, we call it as a what? Aqua. We call it as a what? Aqua. Okay. So followed by, see here, ammonia and aqua. So among these two, which one we have to write first? Okay, we have to write first. Say this NH3 and this H2. Suppose these two ligands were present. So here was starting with N and these are what starting with A. So first preference give to alphabetically for this aqua. So first aqua we have to write, then ammonia we have to write. Understood? So like that here. Understood? So these are what? Writing the formula of the complex of coordination compound. Complex or coordination compound. Okay. So these are what we can say as a general rules. Okay. Now most important part we are going to discuss in here, that is IUPAC nomenclature of what? Coordination compounds. Okay. See, whatever now we saw whatever rules for writing chemical, writing coordination compound or that complex, these are general rules. So it may varies now whenever we are going to discussing in IUPAC nomenclature system. Some changes it will occur. So see, some they IUPAC gave some recommendation also. So how we have to write again this IUPAC nomenclature of inorganic coordination compounds. So say we have to write IUPAC nomenclature of coordination compounds. Okay. IUPAC nomenclature of coordination compound. In that beta rule, you have to write some rule. Rule first, you have to write cation is named first, followed by anion. Cation is named first, yes, followed by anion. Okay. Now rule 2, we can write rule 2. Okay. Rule 2 we have to write naming of ligands. Beta, naming of ligands. Okay. Suppose if you are considering here anionic ligands. So regarding anionic ligands, some anionic ligands which are ends with IDE, okay, and some ionic ligands that are ends with different, okay. So that also we will discuss here. Some anionic ligands which ends with IDE, and that IDE is replacing. Okay, so see here we will write that IDE is replaced by O. IDE is replaced by O. Simply we have to write O. Suppose some anionic ligands I am writing here. Okay, suppose I will write first is NH2 minus. So NH2 minus what beta? Amide here. Okay. So in this coordination compound, how we can write? Yes, simply amido. This somewhere this IDE or somewhere this only E is replaced by what? O. Okay. So like that, say suppose here I will write Cl minus. Okay, suppose say Cl minus. Then what we are writing generally, yes, chloride. Now see here, coordination name of this chlorido. Okay, chlorido. Understood? Means simply whatever here, instead of IDE, suppose if you are considering this E is replaced by O, then it is also okay. Understood? So amide is what? Amido. Chloride is what? Chlorido. Means only E is replaced by here O. Okay. Suppose I will write here Br minus. So Br minus is what? Yes, bromide. As you know what we are writing. Then here what? Bromido. Okay. Now regarding your Cn minus. Cn minus is what? As you know, Cn minus what? Cyanide. But little bit change. Not a cyanido. Here what? Simply cyano. We can call it as a here exceptional, as an exceptional case. S2 minus is what? Yes, S2 minus is, we are writing what? Sulfide. Yes, everyone know this sulfide ion. But whenever we are writing coordination compound, at that time we have to write as a sulfido. Okay, sulfido. Now N3 minus is what? Nitride ion. So simply what we are writing? Yes, nitrido. Nitrido. Okay. So these are some anionic ligands in that E, or we can say IDE is replaced by O. IDE is replaced by O. Okay. Now we will discuss some another anionic ligands. Okay, some another also anionic ligands that we will discuss here with their examples. Okay, so say which are those examples we can consider here. So pay attention. Anionic ligands ends in some anionic ligands. Okay, ligands ends in, okay, ends in ITE or ATE are replaced by, yes, are replaced by E, replaced by this E by O. Okay, so as you know beta, suppose see here this what? Yes, COO minus here and this COO minus. So what we call here? Oxalate ion. Yes, oxalate ion. But this E is replaced by this O. Then whenever we are writing coordination compound, at that time you have to write oxalato. Understood? Oxalato. So this oxalate is converted into oxalate whenever coordination compound IUPAC nomenclature we have to write. So you have to follow this all rules. It is very much important. Okay. See, suppose if you are considering this as the first, second example. Okay, so second example, see, sulfide. What beta? Sulfide. So sulfide is what? SO3 2 minus, as you know. So we can write what? Sulfide 2. What? Sulfide 2. Understood? Now suppose third, if you are considering acetate, acetate as you know, CH3COO minus, acetate. So name, what will be the name here? Acetate. What beta? Acetate. I hope you understood this. Okay. Now suppose if you are discussing carbonate. Okay, carbonate. So carbonate as like this, CO3 2 minus is what? Carbonate. Carbonate. Okay. Now fifth. Suppose if you are considering fifth, nitrite. What beta? Yes, nitrite. So as you know, nitrite is what? NO2 minus. So we can write as nitrate 2. Nitrate 2. Okay. Understood this? Very much important and easy. Okay. Afterwards, we are going to discuss how we can deal with IUPAC nomenclature. First, you have to concentrate on whatever rules. Okay, you have to keep in mind is all names. Understood? With the formulas also, chemical formulas. Okay. Now, some special condition we will discuss regarding neutral ligands. Okay. So say some special conditions. So neutral ligands are named as it is their usual names. Some special names are given to some neutral ligands. Special names. Some special names given to, yes, given to neutral ligands. So we will discuss that, which are those, like this. As you know this, say it is your what, which ion beta. Okay, which ion here? Yes, bipyridyl. Bipyridyl compound. Okay, it is what? Bidentate. Okay, bipyridyl. H2O aqua. Okay, say neutral ligands. H2O. We call it as a what? Water, but here what? Yes, aqua. Ammonia, but here we are writing what? As a amine or amine. Amine or amine. Here what? NO. NO is what? Nitrosyl. What? Nitrosyl. NO2. Somewhere we are writing what? NO2 as a nitrile. Nitrile. Okay. And this bond NO2 we are writing what? We are writing as a nitro. Say the difference. You have to keep in mind this difference. Okay. Now some cationic ligands are named by replacing suffix IUM. Some cationic ligands also we will discuss here. Some cationic ligands. Okay. That in that what will happen, by placing suffix in cationic ligand, by placing a suffix what? IUM in cationic ligands, in some cationic ligands we have to, by placing IUM suffix. IUM suffix and prefix, as you know, suffix and prefix, where you heard this. Yes, when you heard this in your organic chemistry IUPAC nomenclature. Okay, prefix and suffix. Understood? So IUM, see, as you know, we call it as a this, as a what? Ammonium. By placing ammonium, Basically it is a derivative of what? Ammonia and water. So IUM, by placing IUM is what? Ammonium. Okay, this what? NO plus nitrocilium. Okay, now we will discuss here. Okay, these are what? Some basic criteria or basic information, and very much important information whenever we are writing IUPAC, nomenclature of coordination compound, or we can say complex. Okay, now we will start actual naming of complex ions. Okay, say what beta? Naming of complex ion. Naming of what? Complex ion. So in the naming of complex ion, ligands are written in alphabetical order followed by names of central metal atom with its oxidation number in Roman numerals. Okay, this is a very much important part we have to concentrate whenever we are naming of any complex or coordination compound. Okay, so see, right, this very much important. In the naming of ligand, in the naming of ligand, okay, that ligands are written in alphabetical order followed by name of central metal atom with its oxidation number in Roman numerals. It is very much important. Okay, in Roman numerals. Okay, if the complex part contains two or more same types of ligand, okay, so this we can call it as the first. Second, if the complex part contains okay, two or more same type of ligand, okay, then di, tri, tetra, etc. we have to use. For example, we will write here, suppose this cobalt NH3 tri-Cl3 is there. So how we can write here? Yes, cobalt NH3 thrice and Cl3 is there. So how we can use this? Okay, contain two or more same type of ligands are there. Yes, here two or more than same type of ligand, here also and here also. So at that time we have to use this as a prefix. Means say alphabetically we have to arrange. So these are what? Chlorido, and this what here? Amine. So first alphabetically, yes, amine only here will come. Okay, but how we have to write this? Yes, triamine, and what? Trichlorido. Okay, triamine, trichlorido Florido we have to write. It is very much important. Okay. And one more here remarkable point regarding this, or we can considering as here as third point in the naming of complex ion. If the complex part contains more than one type of similar polydentate ligand, okay, more than one type of similar polydentate ligands, when it will come, or similar polydentate ligands are there, okay, then okay, contain more than one type of similar polydentate ligands will come, then at that time we have to use as a prefix bis, tris and tetrakis. Bis, tris and tetrakis we have to use. So it is very much important. Okay, so we will discuss example. So say example, suppose I will write here, okay, Fe, ठीक है, C24 thrice 3 minus. Suppose I will write here example FeC24 thrice 3 minus. So how I will write here? Yes, I will write here tris, because 3 are there, to tris oxalato. Tris oxalato I will write simply. Understood? Tris oxalato I will write there simply. Understood? I hope you understood this all. Okay. Suppose here, as you know, ethylene diamine is what? Ethylene diamine is what? Bidentate ligand. Oxalato, as you know, bidentate ligand, but here 3 are there. Suppose En is 3. Okay, suppose if you are considering here En your thrice in any other complex, so at that time how we can write here? Yes, tris ethylene diamine. Understood? So like that we have to use. So it will when in the case of polydentate ligand we have to use bis, tris, tetrakis, but with the help of monodentate ligand we have to use what prefix? Ditri, tetra. Understood? I hope you understood this all. If any doubt will come, then you can share. Okay, you can feel free to ask anytime. So you remove notes also frequently, you have to revise. Okay, like that one content you have to cover perfectly, accurately and neatly. You have to write in your notebook. So take care, stay safe and stay home. Thank you.